I don't know if the operator could hear me, but I think the batteries are low in the microphone. I'm getting a red signal where I should get green. Okay, it's time to begin. I'm not sure if the microphone is working because it's giving me red and it should be green, but usually somebody will tell me if it's not working. So, okay, this is CSE7315, Planning and Managing a Software Project. And this is what I call Module 0. I always start everything with 0 since I'm in the computer field. And this module covers administrative details. Okay, first of all, here's how to reach me. The first email address is the best one to use, the one that has the course number in it. The second one is a backup number, and I also have a website, but it is not maintained, and I think everything you'll find there is about 10 years out of date, so I'm not sure I recommend you use it. A little bit of background about me. I was actually one of the first computer science faculty members at SMU back in the 1970s. I helped form the department and helped develop a lot of the courses, but in 1977, I left to work at Texas Instruments and worked there. Actually, I started in '74 as a summer employee, and I worked there for a long time, and then I switched over to Raytheon when Raytheon bought part of Texas Instruments in 1997, and I retired from there in 2010. So most of my career was in industry. However, I taught as an adjunct professor, as I'm doing now, all that time. I've been teaching at SMU for about 45 years. And I have seen things change quite a bit, as well as some things that never seem to change. But anyway, so that's a little bit about my background. I was on the technical side of things at Raytheon and TI. I got up to the position of principal fellow, which is pretty high on the technical side, before I retired. And I have been teaching still after I've retired. My specialties have to do with anything related to software development, all kinds of issues which you can see there on the slide. I won't go into them. No, that's not what I intended to do. Let's see, I pushed the wrong button. Okay, a little talk about the class. There are about 15 students. Half of them are in the classroom, and the other half are out there watching by distance education, which is why we're in this studio recording things. Half are taking the course, as I said, by distance education, roughly speaking, and they download the lectures from the internet. Some of these students come to class anyway, if they live in the area, although I've noticed they come when the weather's nice, not when the weather's not so nice. Also, for those of you who are registered in the classroom, if you ever miss a class, it's possible to get permission to read or look at the lectures that are on the internet, which are a recording of the lecture, but I think they charge for them. I don't know how that works, but just in case you want to know. Most of the students in this course are software engineering majors, but there's a few engineering management and computer science majors as well. As a matter of fact, I taught this course once to a group of all engineering management students. All right, the class assumes that you have graduate standing in the computer science, software engineering, or computer engineering, or engineering management area, and it's not required, but it would be helpful if you have had any experience working on real software development, like for a company or for a government agency or whatever. Only because a lot of the things I'm going to talk about here are things that are related to what life is like working in industry, which is different in some respects from what it's like when you're in school. I'm going to talk about many aspects of how to plan and manage a software project. Now, this is an interesting problem because there are little projects with 2 or 3 or 4 or 5 people, and there are big projects with 3 or 4 or 500 people. What I am going to focus on are the larger projects, and the reason I do that is that most of what you learn in school is more suited to the small projects, so I'm going to do something a little different. So you'll learn a lot of things in this class that don't necessarily apply directly for a small project, but if you ever get in charge of a big project, you'll say, boy, I'm glad I learned that. I've had many students tell me that. Okay. The way it's going to work is we are going to have a hypothetical project called Mr. Television, and I'll explain more about that later. And we're going to pretend that you're the manager of the project. It's a software development project, and you're going to write a plan for that project. That'll be the main thing you do in this course. All the assignments are steps in the way toward writing that plan. So, for example, there will be an assignment where you have to estimate the cost of the project. But that cost estimate will end up being incorporated in your plan. There'll be various other assignments that relate to that, and as we'll see. You develop these parts of the plan through various assignments in the course. And at the end of the semester, you turn in the completed plan. But it's not as though you turn in the plan and all of a sudden you get a grade for something that counts 40% of your grade. It's not quite like that. Along the way, there are periods when you turn something in to get feedback. So we'll give you comments. Doesn't count toward your grade, but we'll give you comments like, this part is good, this part isn't good, you need to do more here, that sort of thing. Okay. The way you submit assignments is on the blackboard. If you haven't gotten to the blackboard yet, you need to do that because everything is done via the blackboard. All the assignments are there, all the handouts are there, all the course notes are there, everything is there. And if the blackboard is for some reason unable to help you with what you need, you can send me an email to the course address is better because the way I have my system set up, any email to that email address goes to a special place, and I look at that fairly regularly. Don't ever send anything to me by fax unless I have told you it's okay. And why do I have that strange rule? Well, because in the past I've had students who send me something by fax, and it's a two-sided thing, and they only fax the first side, so I don't see half of it. Or they wrote something on the margin and the fax machine doesn't copy the part that's on the margin, and so I don't see that part. Or they write it in such a light handwriting that when it comes through the fax machine you can't read it. So that's why I try to never use fax. Okay. This is some background. These slides are all available on the blackboard. You can download them. So I'm not going to go over a lot of these detailed slides. This is just numbers and addresses and stuff. The class meets in this room, which is Caruth Hall, room 179C. And anyone who is watching the recording today and wants to come to class next week or something, you'll know where to go. It's in the first floor of Caruth Hall. And there is no class on March 9th. That's spring break. There'll be a midterm exam and a final exam and a course project. The final exam and course project will be due at the end. But the last day of class is May 4th, and I'll give you a week after that to finish everything up. This is some addresses if you need to mail something for some reason. Course consists of 13 lecture sessions and 2 examination sessions. The midterm exam and the final exam, except the final exam will be a take-home, so it's not really a lecture session sort of thing. And I'll say more about that in a minute. The 13 lectures consist of 39 50-minute modules. So each week we cover 3 modules. And this is some more details of when things are done. You can see there are 2 exams which count half of your grade, and then there are 5 assignments which count the other half of your grade. And I'll say more about that in a little bit. Exams are also done using the Blackboard. You download them from the Blackboard, fill them in, and then upload them to the Blackboard. If for some reason you cannot do it that way, you need to let me know so we can make some other arrangement. If you are watching by distance education and watching it through the internet, you have the option of either coming here to campus for an exam, or you can arrange to have a proctor set up, and there's a mechanism for that, which you probably already know about if you've taken courses on the internet before. You don't need a proctor for a take-home exam. Exams are completed on the form that I supply. In other words, it'll be like a Microsoft Word document. It'll say, ask a question, and I'll have a box, put the answer here. You can make the box larger if you need to. You submit the exam by the Blackboard unless there's some reason why you can't do that. For example, the network is down or something, in which case you can email it to me to that address. Worst case, you send it by Federal Express or something, but print it out and send it that way, but that's usually not done. The slides, such as the ones I'm showing you right now, are downloaded from the Blackboard. They're in PowerPoint 2010 format. A very important point about these slides is that they are not going to cover everything. Sometimes I will say something in the lecture that isn't on the slide, but it may be on the exam. So, what you should do is download the slides and either have them on a computer or print them out, and then when you come to class, you should make notes on the slides. So if I say something that's not on the slide, you can write it on there or write it on the back of the page or something like that. The slides are very carefully designed color-wise so that you can print them out in either color or black and white and they'll look okay, or you can just leave them on your computer and look at them that way. There's a whole bunch of handouts. I'll be saying more about that in a little bit. They're all in either Microsoft Word, Microsoft Excel, or PDF. There's a whole bunch of stuff. One thing I want to point out is every assignment has a document called a statement of work, which is a document that says, here's what you're supposed to do, and here's what you're supposed to deliver. In other words, what you turn in to me. There is another statement of work that is called the Statement of Work for the Software Development Plan. Since the Software Development Plan really consists of an aggregate of all your assignments, the Statement of Work for the Software Development Plan applies to the whole big picture thing. Each statement of work has as the very last page of it a cover sheet. And what you do is you take the cover sheet off the back and put it on the front. And that's how I know whose exam or whose assignment I'm looking at. I got into the habit of putting the cover sheet at the very end back in the days when we didn't have the internet and everybody did everything on paper. So they would just tear off the last page and staple it on the front. It seems to work just as well when you're doing it electronically. So that's how it works. Okay, each cover sheet has the assignment number up in the top right corner, so it's easy for me to tell what it is I'm getting. And the reason that's sometimes handy is that sometimes people don't use the right file name, and I don't know what the heck it is I'm looking at, and if I open it up, I can usually see right away, oh, this is somebody's assignment 3. Each assignment and each exam should be turned in by itself, you don't put 3 or 4 of them together and send them all at one thing. You do each one separately. And make sure your name is on it. Every once in a while I get something and I don't have a name on it and I don't know who sent it. There's a document out there called the Submission Rules, which has rules for naming of files and things like that. And you should look at that and use those rules. And let me tell you why. I counted it the other day. I counted that I got 382 emails in one day, which means it's awfully easy for me to miss something from you. So if you follow the submission rules, there's a certain format in which things have to appear. And I have it all set up so that if it appears in that format, it automatically gets sent over to a separate folder. So I get, you're sending in assignment 2. All the assignment 2s automatically go to an assignment 2 folder, so I see them all right there. And I don't have to worry about searching through and finding your stuff. Another point is the file name. Anything you send me that is a computer file, your name should be in the file name. Why? So that if 3 of you send me the same thing, they all have different names, and then you don't overwrite each other, and I know which one is which. Very simple. Okay. The course slides are your textbook. There's some other books recommended that are helpful, but pretty much everything is on that you're going to be covered in an exam or anything is either in the slides or something that I say when I'm talking about a slide. So it's a good idea to make sure you have copies of the slides and that you take good notes during the lectures. There are some additional recommendations in the syllabus document. A little bit about the role of this course. This course is one of 4 core courses in the software engineering program. It's an elective course in some of the other programs. And I just point that out. There's another course that I sometimes teach, 8314. When I teach it, it's usually in the fall. And the reason I point it out to you is, if after taking this course you say, I don't want to ever take a course from that guy again, then you know what course not to take. If, on the other hand, you say, I'd like to take another course from him, then you know what course to look for. Now, I don't always teach that course. Sometimes somebody else teaches it, but those are the only 2 courses I have taught at SMU for the last 10 years or so. That's because adjunct professors like me tend to teach things that nobody else in the faculty either knows enough to teach or wants to teach. So that's kind of where they pull in people like me. All right, so they get to teach all the fun stuff. Stuff that I used to teach when I was a full-time faculty member, and I get to teach all the stuff, but except that I like what I teach, so that's all right. Okay, so that's a summary of the mechanical details of the course, and before I go into the next part of this, which is an overview of the course, I want to escape out of this for a minute, and I want to go over a couple of other things. What does that say? Failure to perform desired action, whatever the heck that means. All right. First thing I wanted to point out is the course schedule. This is something that's available under the syllabus link on the Blackboard. And I wanted you to see this because this is probably a very important document for you to print out and always have available to look at. This talks about on what course day and on what date do I give what module, and what is the subject, which of the 5 assignments this subject pertains to, where in the Futrell textbook there is a discussion of something related to this topic, and if there's an assignment due on that day, the number of the assignment. So for example, assignment 1, which I'll describe later this evening, is due next week. I like to get you started early because there's a lot of work to be done. You might as well get started on it. Assignment 2 is due 3 weeks after that. Assignment 3 a few weeks after that. A big advantage of assignment 3 is you have spring break to do it. Then there's a midterm exam, and then assignment 4 is due a few weeks after that. So they're fairly well spaced out. And then assignment 5, which is the complete plan that I described earlier, has to be turned in at the end of the semester. I mentioned that essentially all assignments relate to this plan you're developing, and that's what this right-hand side is all about. What it says here is, whoops, what happened there? Sometimes I lose track of the mouse, and I don't know what happened to it. Well, there it is. Come on. There we go. When they have a white mouse on a white background, it can be hard to see it. The software development plan, as I said, is a plan for the project, this hypothetical project that you're going to develop using information you learn from the lectures and from various other assignments and so forth. Well, this right-hand column says which part of the plan corresponds to which topics. And so that kind of helps you understand what part of the plan you should have at least done a first draft of by what date. Okay, so that's what I wanted to show you with the schedule there. The other thing I wanted to show you is the, where is it? Oh, here it is. There it is. This is the blackboard. You should have already been there. There's a whole bunch of announcements, and in particular, everything is out on the blackboard except some of the course slides aren't out there yet, and this little announcement will tell you when they're available. There will be other announcements as we go through the semester. The syllabus folder, or syllabus link here, has the syllabus, and I'm not sure why they're, oh yeah, the syllabus, the schedule, which I just showed you, the submission rules, which I mentioned earlier. Now, the student profile, about 2/3 of the students in the class have sent me their student profile. If you haven't done so yet, please do so. You just take this file right here, it says student profile, and fill it in and email it to me. And the reason I want that information is that it gives me a little information on the background of the class, because every year I teach this, the background is a little different. And I like to emphasize some topics and modify things a little bit to fit the class. So if I notice that everybody has a certain kind of background, I might make a slightly different way of teaching some of the topics. So that's why I need that. But there's another reason I need the student profile, and it's a very practical one. At the end of the semester, early May, sometimes I find myself in a situation where I need information from you, or I don't see any record that you submitted one of your assignments, or there's some other problem, and I need to reach you very quickly. Well, the student profile tells me how to reach you, and that's sometimes very, very helpful. So that's the thing. There's the welcome memo, which I think the secretary sent to you anyway, but that tells you a little bit about the course. Then where it says faculty information, that just tells you more about my background. Course documents, this has handouts, the course slides, information about getting a grade of incomplete. You probably don't need to worry about that till the end of the semester, and then you say, wait a minute, I can't finish on time. That happens sometimes, and if that's true, then this information will be useful to you. You click in here, you get all the class slides, and as you can see, I only have the first 3 up there right now, but I'll put some more up there later. Okay, now there's another link here called assignments and exams, and it has a folder for each assignment containing the stuff you need for each assignment. There's also 2 midterm and final exam. You'll notice it says availability is not available. That means when you log on, you won't see it. Only the instructor can see it. But eventually the exam will show up there, okay? All right, now let's see here. I want to look, there's one other thing I'm looking for. Okay, I don't see, let's see, okay, look under handouts. Let's see, oh yeah, okay. I want to point out the handouts. The general handouts are general things like general background files that may be useful for some of the assignments, okay? Now, almost everything else is related to the Mr. Television project, this pretend project that you're going to do a plan for. There's the statement of work for the software development plan, which applies to the whole thing, all 5 assignments. There's information about the technical aspects of the project, and there's information about policies, meeting notes, and other managerial aspects of the project. There's also a sample midterm exam, which is not yet available, but somewhere along the line I'll put one out there. When you are planning to do the project, planning to do the course, you're going to need to look through all this material, and you will find it very useful as you go along. Okay, that's that. Now, how do I get back to where I was? It's one of the weird things about computers is they can't help but ask you to do stuff. Okay, now we're going to go back to the course overview. All right. Software engineering process is what you do when you develop software. It's the things you learn when you learn how to program, or you learn how to do data structures, you learn how to do design, all that stuff. It's the technical part of doing software. Management really consists of two things. There's the general management issues, which is represented by the orange thing at the bottom, and there's risk management, which I represent as the blue thing at the top. And this course is going to focus on those two management boxes, but it's also going to talk some about the part of the middle, mainly from the point of view of if you are in charge of a project, what sorts of things do you have to be paying attention to? The sort of central idea here is that you pay attention to the process you follow when you develop software. How do you go about developing software? What do you have to put in place? If a manager wants to manage a project, the manager needs to know what's going on. How do you know what's going on? Well, we'll talk about all that. Now, there are certain other aspects of project management that I am not going to cover very much in this course, but I wanted to mention them because they are important. I'm not going to talk about people issues. In other words, how to hire the right person, that sort of thing. We're not going to cover that in this course. Methods and procedures, the details of how we do it. This is because that is covered in other courses. You want to know the details of how to design software, there's courses on designing software and so forth and so on. If you want to learn the details of how to test software, there's courses on how to test software. What we're going to cover in this class is what does a manager need to know or a team leader need to know about what's going on in those areas. The resources you need to do the work, the computers, the software, the test equipment. We're not going to spend a lot of time talking about that. We're not going to talk about how to choose the best compiler or anything like that, but that is something that will have to be done on a real project. We're not going to talk a lot about the things you produce during the course of performing the work, other than I'll give you samples of some of these things, and you will be producing one of them, namely the plan. Along the way, you'll be producing other things like estimates. There's also a big issue with regard to management, and that is communication. You have to communicate with lots of people. You have to communicate with people you work with, people you report to, people you don't even know but who are doing things that affect what you're doing. We'll see more about that. What this course focuses on is three things: planning, managing, and improving. Planning means figuring out what you're going to do. Managing says doing it and keeping on track when you do it. In other words, one of the first things you'll find when you start managing a project is that the plan wasn't perfect, and you will need to make corrections, and we'll talk about that. And finally, improving the way you do things. One of the things we will spend a lot of time on is how to collect information that will help you do better the next time. Why? Because if you're going to have a career in the computing field, sooner or later you're going to be managing projects, and you're probably going to manage more than one. Unless you do a really miserable job, in which case they'll demote you and you won't ever get a chance again for a while. So the idea is you better learn the first time how to do better the next time. Let's talk about planning. Planning includes a lot of things. It includes understanding what you're supposed to do. This is not just what product are you supposed to make, but what are the customer's perspectives on this? Sometimes what the customer sees as their need doesn't match the requirements that you've been given or the information you've been given. Then organizing. How do you put it together? How do you build? It's like designing your project. Then selecting some of the specifics of your project, the product development lifecycle, the process to follow, the languages, programming languages, the tools you're going to use. Then defining the work to be done. This is a really important part of management. Saying, here's all the steps we have to carry out. Estimating what it's going to take to do all that work, and then documenting all that in one fashion or another so other people know what your plan is. And again, the major assignment of the course will involve doing all of these things, and ultimately you'll produce the plan. Now, a lot of the time people tell me, well, in my organization we don't develop fancy plans like that. Well, that may be. Maybe your organization has never done a really big project. But here's what happens on a big project. Let's suppose you get a project to develop a bunch of software for a really big deal, like NASA wants you to develop software to manage a space station, or the government somewhere in the world wants you to build an air traffic control system, or automobile manufacturer wants you to build the electronic system for an automobile. Anything really big like that. When that happens, how do you think they decide who to give the contract to? Well, there's a lot of people who claim they can do it, but if you're going to spend millions of dollars getting that software built, you're probably going to do some assessment of the various potential contractors. And one of the ways they do it is they say, I want you to give me a plan that tells me how you're going to do this. And it's usually a written plan. Now, how do they use that plan? They first of all determine whether you sound like you know what you're doing, and whether or not you have a reasonable approach toward it, and have you done a reasonable assessment of the issues, the risks and the opportunities, etc. And so a document like a plan is necessary in that kind of a situation. Well, that's very similar to why I'm having you write a plan in this course. Because I'm playing the role of imagine that I am trying to hire one of you to run my software project. And the way I'm going to decide is I'm going to look at the plans each one of you wrote and decide which one of you seems to be the best one. Now, it's actually not going to be quite that bad. There will be more than one A given out in this course. So there will be several of you who have good plans and will get good grades because your plans are good. But that's the way I evaluate the plan. I evaluate it by saying, does this person sound like they know what they're talking about? Does this plan make sense? Did they take all the issues into consideration? So that's why I have you do this plan. There are many, many situations in big projects especially where you have to write written plans. And I'll say more about that later in the course. Okay. Managing execution consists of setting the right framework, so everybody knows what you're supposed to do, identifying and managing risks. That's a major, major activity. You'll find that about 25% of your grade on the final plan will be, one way or another, derived from how effectively you've analyzed the risks and done appropriate things about them. Measuring to monitor progress. Managing the configuration, we'll talk about that a little bit later, and revising and updating the plans. It's a lot like piloting a ship. You are constantly making mid-course corrections, making sure you don't run into any icebergs and things like that. And you may have a plan, but you change the plan over time. And that's what we're going to be talking about. The third step I mentioned is improving the way you do things. There's a field of study called quality engineering, which is really what my other course is all about, 8317. It's all about designing the product so that it is of high quality. And some aspects of that are critical to managing any project, and that's the part that we're going to focus on in this course. And one important part of that is measuring what you actually did compared to what you planned and learning from that. So for example, let's say there's a part of the project that you say, I estimate it this will take 3 weeks to do. And after all is said and done, you say, you know, that actually took us 7 weeks to do that. Well, then the next time you plan a similar project, that information will help you do a better job of estimating that part. So we'll talk more about that too. This is one of the things you will see every once in a while, a little quote from a book called The Dilbert Principle. The Dilbert Principle is a book written by Scott Adams, who writes all the Dilbert cartoons, which some of you may be familiar with. Dilbert cartoons are cartoons about the frustration of being a competent technical person in a company run by idiots. And their managers are always stupid, and the technical people are always smart, except sometimes they have their own little weird quirks as well. And the reason I use these quotes is because when you are in a position to be a manager, you want to say to yourself, am I doing something stupid? Am I doing something that the employees look at me and say, you're doing more harm than good by making us do it that way? And so you'll notice this quote here. The biggest obstacle to the success of any project is management itself, because management supports the project by demanding frequent status reports to explain why you don't have enough time to meet your deadlines. And of course, the reason you don't have enough time to meet your deadlines is you're spending all this time writing status reports. So the idea is, if you're going to demand status reports from your employees, you need to make sure you don't do so in a way that is overly burdensome. You want it to be something that's easy for them to do, so you're not taking a lot of time away from them getting their real work done. That's what this quote is really all about. I mentioned this assignments, and let me just briefly go through them again. The first assignment is a work breakdown structure, which we're going to talk about, for doing this course. There's also a thing called the Earned Value Workbook. And the Statement of Work for Assignment 1 has extensive information about how to do this, and there's also a template that you can use as a starting point for doing this assignment. Basically, what this assignment consists of is making a list of all the work you have to do to take this course, breaking it down into measurable units of work, and then organizing it in a particular way called a work breakdown structure, and then estimating how long it'll take you to do each part of that, and then estimating when you will do each part of it. That becomes your plan for taking this course. Then, as you take the course, as you go through the course week after week, you will, well, I've got the wrong button here. There we go. As you go through the course week after week, you will record how much time you spent on those various tasks and which ones you finished. And there'll be some graphs that will automatically be produced that will tell you where you are relative to where you should be, so you can track and manage your own time. You get 3, 4, 5, 6 weeks into the course and you say, I'm way behind, I better spend more time on this course. Or you may be way ahead and say, no, I can slough off. Whatever it turns out to be, you can track your progress. And learning how to do that is what that assignment is all about. The grade that really matters on that assignment is the one you get at the end of the course. It's worth 15% of your final project, is how well you do that assignment. Okay, the second assignment is a draft of your software development plan. And there's a lot of details that will not be there yet. But the idea is it's a rough draft. You'll turn it in. I will evaluate it. I'll tell you, you're doing this part right. This part isn't looking so good. Why am I doing this? Because this is what happens in industry. You don't just write a big, thick document and turn it into somebody without anybody else looking at it. You write a draft, send it around, and your friends and people look at it and say, this part's unclear, this part's missing, whatever. And that helps you do a much better job with the final version. So that's the way we model it here. Assignment 3 is a size estimation report, where you're going to estimate the size of the software. 4 is a cost estimation report, where you estimate the cost of the software. And then the 5th assignment is the whole plan, which is a big chunk of your grade. Okay. The software development plan is the major assignment of the course. It is a plan for managing this project called Mr. Television. It's going to say how you're going to organize it, what the schedule is going to look like, how you're going to go about doing things. And every piece of the plan is something that is covered somewhere in the course, somewhere in the lecture material. So as we cover something in the lecture material, you should be able to learn what to do about that part of the plan. The statement of work for the plan defines all the things you have to do and what you have to deliver. The deliverable is the plan in a particular format. I say 100 to 200 pages. Ideally, the plan would be 100 pages, roughly. Some students have turned in plans with as few as 50 pages, but in almost every case, they've gotten not very good grades because they left important things out. Some students can't help themselves and they end up writing a lot more than 100 pages. That's why I put the 200 there, because sometimes I get them. The worst I ever got was 323 pages. That was a student who really loved to write. He didn't necessarily get a better grade either. He took 4 pages to write what most people would do in a page and a half. So that's the way it is sometimes. The tasks you do throughout the course is you study the topics as we teach them in class, and then work on the corresponding parts of the plan. You submit a draft of the plan, or actually the first part of the plan, by assignment 2, which that's due about week 5 or so. Complete major appendices to the plan in assignments 3 and 4. That's the cost and size estimating. And then finish everything else by assignment 5. That's how the work is laid out. Now, I have this phrase: the sooner you get behind, the longer you have to catch up. And you're already behind, so you have plenty of time to catch up. That's what I'm really saying is, don't put it off. Those of you who haven't done your profile yet, do it. Those who haven't looked at any of the class materials, you better start looking. This class is already the very last time slot in the whole semester for SMU. Every other course has had at least one class session. And the reason is because of the holiday a week ago. But anyway, so you need to get moving. Okay, a little bit about the plan, roughly 100 pages. I recommend you look at the cover sheet for assignment 5 and see how many points there are for each topic. If you have a topic that's worth 10 points, you probably figure you ought to spend more than a half a page on it. Whereas if you have a topic that's worth 2 points, maybe more than 3 or 4 pages is too much. And that's just a very rough guideline, but it's amazing to me sometimes what happens is, let's say a student is very familiar with testing because that's what they do in their regular full-time job. So their section on testing is 14 pages long when all I needed is about 2.5. And then their section on some other thing that's really important is only 1 page because they don't know much about it and didn't study it very well. So one other point, use 1.5 spacing for most of your text, but in tables or figures, do single spacing. Otherwise, they end up taking too much space. The statement of work tells you how to lay it out, and there's a template that has all the different headings and everything, so you just have to fill in the contents and delete all the parts that are guidance. In the template, there's a lot of sections that are guidance to you, and it's easy to tell what those sections are, and you just delete that. That's telling you what to put here. Be sure to number all pages and put your name somewhere in there, preferably in the header or footer, so I can figure out whose work I'm grading. How do you develop the plan? It's evolutionary. You start with the template and start replacing parts with real material, and over time you add better material or make improvements. That's the way you do a plan like this in real life. The course has one recommended but not required textbook. That's the one by Futrell. It's recommended because it has a lot of material that supplements what's in the class notes. There's a lot of reference books in the syllabus, but there really is no book that exactly covers the material the way I cover it. That's the Futrell book. And I point out the Watts-Humphrey book because it's an important book, even though it's many years old now. It's considered a really important book on the subject of managing projects. Okay, let's talk about assignment 1 a little bit. To prepare a personal earned value workbook. This is a workbook is the term Microsoft uses for what I used to call a spreadsheet. But what it is it's a document that has multiple tabs, and each tab is a separate spreadsheet. That's why they call it a workbook. So there's a first spreadsheet is a personal work breakdown structure. The second one is the actual worksheet. The third is the earned worksheet, and then the last one, the other ones are graphs. This is the thing that you use to document your plan and then plan the course. You really need to use a tool like Microsoft Excel to do this. If you don't know how to do it, this is the time to learn, because if you're going to do any kind of management, you're going to have to use spreadsheets. What you submit for assignment 1 is the workbook completed as of the end of the second week of the course. That's when you turn it in. And it should basically reflect the work you have done for assignment 1, because that is assignment 1. But there's the rest of the assignments for the course would be reflected in there. And then you update it every week, and you can turn it in with later assignments if you wish, and then we'll give you feedback on whether you're doing it right. The submission rules document is out there, but some of the key highlights is that every email or file that you submit has a code, and the code begins with what it contains or it pertains to. A1 is assignment 1. Then the course, then the year and the semester, and then your name. And the reason for that is so I know which student submitted it, what assignment it's for, and I can put it in the right place. All right, to summarize this module, the course covers the tasks needed to plan and manage your software project. The project is to develop a software development plan. That's the hypothetical project that you're going to use in this course. And the personal earned value workbook is how you keep track of your progress. Now, I know it says the end of the module, but we actually have a few minutes left. And what I'm going to do at this point is I'm going to see if I can find assignment 1 and show you something here. I want to find the template. There's the template. By the way, there's also a frequently asked question and a statement of work, and then a template. Now, you'll notice that there's a cover sheet here, so you can put your name in here and all that kind of thing. And you'll notice it also tells you how many points each part of it is worth. This is your personal work breakdown structure. And I want to say a few things about what this is all about. So let me make it a little bigger here. Personal work breakdown structure is all the work you have to do assignment 1 and then assignment 2 and then assignment 3. And in most cases, I've left plenty of room for you to insert new information, because part of assignment 1 is for you to analyze all the assignments in the course and figure out all that you're going to have to do to complete all those assignments, and then put all those tasks in the work breakdown structure. We're going to say more about work breakdown structures later. Here, you put when you think you're going to do each of these tasks, and just do it by week number. This is week 1. Then, how many hours you think you're going to spend on it. This part here, from here to here, becomes your plan. This is your plan for taking the course. Then over here is where you put reality. When you actually finish it, you put what week you actually finished. When you are working on it, you put how many hours you've spent so far and how many hours you think are remaining. And over here on the far left, there's a little thing where you put the status of the task. It's open means you haven't started it yet. If it's in progress, it means you're working on it, but you haven't finished yet. And if it's complete, that means it's all finished. And in that case, estimated hours remaining should be 0. Now, there's instructions about all this, and I'm only giving you sort of a very big overview here. But the idea is this tab right here, Personal Work Breakdown Structure, is your plan for taking this course. The actual file over here, this is a spreadsheet that has almost exactly the same structure on the left. And the difference is every week you record how many hours you actually spent on each task. Then, when you have finished with that, there's a thing called a burn down chart. And the burn down chart, the red line represents your plan for getting all the work done. The green line represents where you are as of today. If you follow the instructions correctly, as you go through the course, you will know where you are relative to your plan. Very, very simple way of keeping track of your overall status. Now there's another section here called the earned chart, which looks identical to the actual chart, but it's not quite. The number you put in here, you don't put anything in here until you finish. And then when you finish a task, you put your originally estimated amount of hours in this cell right here, the week when you finish it. So instead of recording actual hours spent, you record the estimate for that task, and only in the week when you actually get the work done. That will lead to this other graph, which is called the earned value graph, which is actually a burn-up chart. And what you'll see is, and we'll talk about this later in the semester, this chart will give you a deeper insight, not only as to where you are, but as to why you are where you are. In other words, if you're running behind, it'll tell you it's because you're not spending enough time, or it's because you're spending enough time but you didn't estimate correctly. And it'll help you decide what course of action to take. We're going to talk about all these things later on in the course, but I wanted you to see, I'm giving you this template to start with. So all you have to do is modify the template to describe your task of taking this course. So that's assignment 1, and now it's time to take our break. I'm not going to save this, so we're going to take a break until 7:30, which is about 9 minutes from now. There we go. Okay, now we're going to cover Module 1. We're going to talk about the role of process in software engineering. It says more on Assignment 1 classroom demonstration, but that's what I actually did at the end of the previous module, so we can skip this, which may mean we can get out early tonight. We'll see how that goes. This is the title of the course. This is perhaps a more honest title because this is what often happens when people try to manage a project. It becomes a disaster because, as one student told me, I wish I had taken this course before I managed a project instead of afterwards. Here's a Dilbert quote I'll let you read. Now, what he's really trying to say here is projects can be very stressful, and especially for the person who's leading the project. I want to talk about the importance of a process in running a project. A process, I want to begin by defining it. And one of the interesting things about the word process is that different people have different definitions. Watts-Humphrey defines process as a set of tools, methods, and practices used to produce a product. Futrell says it's a bounded set of interrelated activities and uses a lot more words to say what he wants to say there. What I define it as is what happens when you do a task. Now, my definition comes from my background in writing operating systems. In the field of operating systems, a process is some activity that occurs. And that's really where my background comes. All of these definitions are really talking about different aspects of the same thing. A process is something that happens over a period of time that involves activity, such as swimming is a process, walking is a process, sitting in class is a process, although not a very active one. It's a dynamic thing, and what I mean by that is that if you do it twice, then it's considered two different instances of the same process model, technically speaking. So if you go swimming today and then you go swimming tomorrow, even though you swim the exact same place and the exact same distance and the exact same time, it's two instances of swimming. If you sit through class 3 days in a row, that's 3 times you sat through class. And it's important to understand the difference between the description of the process and the actual activity involved in a process. The description is usually called a process model. It is sometimes called a representation. So, for example, a description in a book of a like suppose you had a book on how to swim. That would be a process description. Whereas going swimming is the actual activity of swimming. Now, a computer program, it turns out, is a process description. It tells you what the computer is supposed to do. Whereas when the computer does it, it's a process. And if the computer does it 5 times, it is 5 instances of that same process description. And that's an important distinction, but you'll find that when you read papers and you read articles and you read things on the web about processes, very often the authors confuse these two concepts, the description of the process versus the actual activity of doing a process. So think of the description as like the book on how to swim. The process itself is swimming. Here's some other examples. A book on how to hang wallpaper is a description of a process. Actually attempting to hang wallpaper is carrying out a process. Cooking a meal is the process. A recipe is a description of the process. The recipe says, here's how to cook this meal. Whereas when you actually cook the meal, that's the process. And again, it's a distinction that many don't necessarily pay a lot of attention to, but I think it's important to understand the difference, because the description is a static thing. It's a here's how to do it kind of thing, whereas the actual activity itself is an active thing. A process generally has a beginning and an end, although you could have an infinite process, one that runs forever. Every time you make the process happen, it's called an instance, and sometimes people use the word instantiated or executed or enacted. There's all kinds of fancy words people use. But what it means is you are making the process happen. Now, a process description can be either a recipe for how to do it, or it can be a description of what actually happened. So let's suppose you have a book on how to hang wallpaper, and then somebody tries to hang wallpaper, and then you have a picture of what happened when they tried to hang the wallpaper. They didn't do it very well in this example. So this is a description, this is a description, and this is the actual process of doing it. That distinction will come up from time to time as we go through the course. Now, I want to make another important distinction between a tool, a method, and a process. A process is, in rough terms, something that tells you what to do. A method is a how to do it, and a tool is something to aid you to make you do it more efficiently. So, for example, something that says the way you design the software is you design it, then review the design, and then do an update on the design. That might be a process. A method might be object-oriented analysis. That is a way of designing, or object-oriented design, I guess would be a better word. A tool might be a compiler or a measurement tool or a test generator. Now, why do I make this distinction? Because very often people don't appreciate the difference between these things. For example, they think if they get a new tool, they can do a better job. Now, let's suppose you have somebody who doesn't know how to use a computer, and you buy them the fanciest computer possible. That won't necessarily help them do anything, because they have a tool, but they don't know how to do it. Whereas a course on how to use a computer will tell them what to do and how to do it. And there's a famous quote, if you automate without a process, you screw up more efficiently. It's like, if you don't know what you're doing, then giving you a tool to do it with doesn't necessarily make you any better. Now I have an example of that. A tool without a process is like a fast car with an inexperienced driver. Let's say you have a child. The child is 16, wants to learn to drive. And you say, okay, well, I don't have time to teach you how to drive, so I'll just buy you an expensive car. That probably won't work, right? You need to teach them how. Now, this is a true story. I got it from several sources. A father bought a new Ferrari. His daughter wanted to borrow it. I can see where there's problems already. Here's what happened. She hit a power pole at 200 miles an hour. She was wearing her seatbelt, so she wasn't hurt seriously. But the car didn't survive. It cost $1 million because he had to pay for the pole she knocked down in addition to the car. And it was a 2-year waiting list to get another car. It had 9 miles on it, one of which occurred during the wreck. So, that's sort of an extreme example of why you don't solve a problem by giving somebody a fancy tool. You have to teach them how to do what you want them to do first. Now, let's suppose you have a child who knows how to drive. You've given them driving lessons and taught them how to drive. But in the meantime, they have not studied geography, so they don't know where anything is. So they know how to do it, but they don't know what to do. So you put them in the car in Dallas, Texas, and you say, I want you to drive to California, and they start heading east because they don't know anything about geography. They are an excellent driver, they have a great car, but that still doesn't get them where they want to go because that's where they have a method, namely how to drive, but they don't have a process, which is the what to do part of it. Process is important because process tells you what you need to know what to do with the skill that is represented by your method. You won't get to the right place fast if you don't know what you're supposed to do. Suppose you have the world's 10 best programmers and they work for you and you tell them, just start coding. And I'll tell you what you're supposed to code next month. Well, it won't do any good. They may be great programmers, but if they don't know what they're supposed to do, that won't help any. A process gives you knowledge. It tells you where to go, how to get there. And one of the most important things about a process is it tells you what shortcuts make sense and what shortcuts don't make sense. And the risks of various options so you can make informed decisions about how to do things. This is the difference between an experienced person and an inexperienced person. An inexperienced person not only knows how to do it, but they know more than that. They know about special cases. Now, how do you describe a process? How do you document a process? Well, it depends on who's going to use the process. We've already mentioned that a computer program is a description of a process. But you probably wouldn't want to give a computer program to a person and say, this is how you do your job. If you could do that, you might as well use a computer to do it. But let's talk about what are the essential elements of a process description. The tasks or activities that they should perform. The artifacts, that is, the things they use or the things they produce. The inputs and outputs. And the relationships and sequences among all of these. Do this first, then do this. Think about a recipe. It has ingredients, which are the artifacts. It has things to do. Cook this, chop that, whatever. Those are the tasks. And it has an order. Chop this, then mix it with that. There's an order in which things are done. The process description must include the tasks, that's the what to do, the sequencing, that's the when to do it, and the information, the data. And that's exactly what you have in a computer program. You have executable statements, which are the tasks. You have statement sequences like conditional statements and loops and go-tos. That's the when part. And you have data declarations, which tells you about the data. Now, if a person is going to be using a process, there's optional information you may want to include that you wouldn't have to include for a computer. For example, comments and documentation. You may or may not want to include that. Why do you include comments in your computer program? Not for the computer's benefit, but for the benefit of the programmer. Entry or exit criteria. What does that mean? It means information that helps you decide whether it's time to do this, and information that tells you whether you're done or not. For example, a recipe might say, cook this till it gets brown, or cook this till it changes color, or till it thickens, or something like that. Why you should do it. Now, you don't need to tell a computer why the task should be done, but you may need to tell a human. If you tell a person, I want you to go do something, they might, being a human, might say, well, why should I do that? Who should do it, or maybe what skills are needed to do it? Who needs the results? Who cares about doing it or not? What you should measure along the way. Any risks associated with doing that. For example, in a recipe, you'll often find something that says, be careful not to do this too long or this horrible problem might occur. And you might have references of additional information. This is the kind of information you need to supply to the people who have to use the process. So exactly how you represent a process depends on who is going to use the process. And that's important. The reason I emphasize this is because very often if you're in a managerial position, you have employees and you want to tell them how to do their job or what to do. Well, you have to think about how can you explain it in a way that they understand it. Sometimes people describe things in ways that make sense to them, but that the people working for them don't know what they're talking about. So that's why I'm talking about this. Wow, that's not the end of Module 1. Sorry, I keep pushing the wrong button here. That's what comes from using computers for too many years. Okay. Every once in a while you're going to see a slide like this. It says possible exam question. And this is a question that might or might not be on an exam. It's simply to get you thinking. You should be able to answer that question. Notice, by the way, it says use examples. When I have an exam question, I like to pose it in the following way. I imagine that I am a colleague of yours who wants to know the answer to something. And I want you to explain it to me using an example so I understand it. That's really all it involves. I find that if you can come up with a good example, that means you understand it. That's why I ask the questions that way. The goal of a process representation is to be specific enough to enable a correct outcome, but flexible enough to allow judgment. So, for example, a map tells you how to get somewhere, but it doesn't tell you exactly what speed to go, and it doesn't tell you that you have to do it in this way. You could maybe go this route instead of that route. And similarly, a recipe will tell you what you have to do, but it won't necessarily tell you a lot of details that aren't terribly relevant. Although it may warn you if it is important. Like I've seen recipes that say, this will not work if you double the recipe. That's an important piece of information. A good recipe is specific enough to enable correct outcome, flexible enough to allow judgment. Although it's interesting, if you look at a recipe book intended for a novice cook, it'll be a lot different from a recipe book intended for an experienced cook, because they assume the experienced cook knows more and doesn't need as much specific guidance. You need to think about this if you're in charge of the project. How flexible versus how exact are your instructions to your employees? When you tell them you need to do things a certain way, do they understand where they have leeway and where they don't? A computer program is very precise. A computer program doesn't give the computer too many options. You know, add this number to this number, and that's all there is to it. Because a computer doesn't have the ability to exercise judgment, although if we get into artificial intelligence, maybe that's not true. A human being needs a degree of latitude, and there's a big difference between a human being who's doing manufacturing work in a factory, which needs very precise instructions, and a person working in a research lab who needs relatively imprecise instruction. Here's the way you would describe how to cook 2 eggs if you're describing it for a robot versus if you're describing it for a human being. Most human beings could take the one on the right. Most robots would need the one on the left. So you have to pay attention to who it is that you're writing the description for. Human processes rely on flexibility and human judgment. But if you give them too much flexibility, you can get chaos. This is one of the risks of agile development. Sometimes people interpret agile development to mean no rules, and then they can get themselves into trouble because they've produced not very good software and they don't have a very organized way of going about their business. On the other hand, you don't tend to get too rigid with people. So you have to know the people in order to know how rigid to be. Now, why am I spending all this time on processes? Well, people have studied projects for years and why they fail and why they succeed. And they have found that there are many, many factors, but one of the biggest factors, by the way, is communication or lack of good communication. You don't pay enough attention to what's going on elsewhere. You don't listen to the customer enough. You don't talk enough to the other people involved in other parts of the project. But one of the other major mistakes people make is not having good processes, not having paid attention to the what do you have to do part. It's a core issue behind successful software development. Now, doesn't mean it has to be complicated. It doesn't mean it has to be bureaucratic. It means you have to know what you're supposed to be doing. Now, here's an example of a typical software problem. It costs more than it was anticipated to cost. This is a true story. They planned a database for $250,000 in 9 months, spent $2.5 million in 2 years, and they still needed another $1 million to get finished. Not at all an unusual case. It's kind of like students saying, yes, I can take this class and I'll get it done in 8 weeks, and then they get finished 2 years later. But anyway, the point is, why did this happen? Well, it could have happened because they didn't know what they were doing. But it could also have happened because they didn't know how to estimate the cost very well. Maybe any competent software team would have taken $3.5 million. Another reason they might have made that mistake, if it was a mistake, is that maybe they knew they would never get $3.5 million, but if they bid $250,000, then they'd get the contract, and then they could keep asking for more money. There is a true story I want to tell you if you've ever been to the University of Pittsburgh. There is a big, tall building called the Tower of Learning or something like that. It's about 12 stories high or something like that. And the architect who was responsible for it knew that the Pennsylvania State Legislature was not going to give him enough money to do it. So what did he do? He had them build the steel infrastructure, and then he had them build out the top floor first. And he got down to about the 7th floor and ran out of money. And he knew the state legislature wasn't going to leave a building completed. In other words, if he had gone from the bottom up, they would have said, just seal it off and that's the end of the building. But when he went from the top down, they knew they weren't going to leave 7 stories of empty space except steel girders, so they gave him the money to finish. Anyway, so that's a guy who knew about how to manipulate that sort of thing. But anyway, so there's various reasons why you might have not estimated the right amount. Either they didn't know how to estimate it properly. We're going to talk about estimating. They didn't have enough information to estimate properly. We're going to talk about that aspect of things. The requirements changed significantly after they started, and we're going to talk a little bit about dealing with requirements and other changes. Or they didn't know how to develop the software properly, and we're going to talk about managing development so that you are less likely to have that problem. Now, the point is, when it costs more than it should have, it could have been any of these 4 reasons, or perhaps other reasons that aren't on the list. You don't just automatically assume that it's because they didn't know what they were doing. This is a big problem often in government contracts. Government contracts are often, you'll see a big headline. It was supposed to cost $10 million, it cost $30 million. Well, maybe that's because Congress kept changing their mind. This happens a lot. I know, I've worked on a lot of government contracts. You think you know what you're supposed to do, you get started doing it, and then they change their mind and they want to do it differently, and you got to do it you got to do all that work all over again, and that's why it costs so much more money. On the other hand, sometimes it is because you don't know what you're doing. So it just depends. Let's talk about the case where it costs more than it should have cost. In other words, you should have been able to build it for a smaller amount of money than it actually cost. It could be because you didn't know how to develop the software properly. It could be that you added unnecessary features that weren't required. We're going to talk a little bit about that. It could be that you used contractors who didn't know how to do it properly. Sometimes the problem is not you, it's your contractor you hired to do the work for you. Or it may be that you didn't know how to manage your contractors. You hired somebody to do it but didn't know how to manage them properly. And we're going to talk about that. Now, another common problem is software doesn't meet its requirements. For example, a payroll system only delivers half of the promised features. This is a common scenario. One that I ran into because it affected me very directly. I was working for a computer company back in the mid-1980s. A whole bunch of people left the company. They were artificial intelligence experts. They went off to build a computer-aided design system using artificial intelligence. And they had this wonderful, beautiful design, except that it was so slow nobody would buy it because they hadn't paid attention to the customer's need. The customer didn't care whether you used artificial intelligence. The customer cared whether it ran fast. It's like you use a computer. You don't know whether the software on that computer was written in a quality manner. You just know that it either works or doesn't work. You don't care whether it was documented properly. You don't know, and they won't show it to you, so maybe you have no way of knowing. Software fails to meet standards of quality or safety. For example, very famous case of the Therac X-ray machine that gave a 10,000 times dose of radiation because of a software bug. Killed people. Why? It wasn't properly tested. Very serious problem. We all know of bugs in our smartphones and in our PCs, et cetera, et cetera. We all know of security problems. There's all kinds of examples today. The public at large is pretty much aware of the flaws in many computer programs today. 30 years ago, that most people didn't even know about these things. I had a student in this class a few years ago who worked for a company that made computers that were connected to smart water meters. And the way it worked was you drive around and you could read the meter without having to get out and walk to the house and look at the water meter. It was done through data communications. And he said, they intentionally produced buggy software. Why? Because they had a service contract that they sold to all their customers that they made a lot of money off of, and they wanted to have the software have enough bugs that the customer would buy the service contract. So they intentionally put errors in the software. So there's all kinds of stuff out there. Software causes unanticipated results. This is one of my favorite ones. An insurance company had software for processing claims, and it accidentally spent $60 million in double payments. 35,000 policyholders quit because they figured if they quit, they could keep the money. So not only did they pay out the extra money, but they lost all these policyholders. Lots of examples of this. The core message is that if you're going to produce good quality software, you have to pay a lot more attention to management of the development of that software. It gets to the basic principles of management, which is that you focus on the process. You don't just worry about how you write good code. You worry about the whole thing, which is really what this course is all about. Here are some principles to keep in mind. The first one is the quality of the product is determined in large part by the quality of the process used to develop and produce the product. In other words, if you don't have a good process, you shouldn't be surprised at poor quality products. It doesn't mean you can't produce good quality products. But what it most likely means is you will not get consistently good quality. Some will be good, some will not be so good. You can't rely on it to be a very good quality. Another one is the way you improve quality is you define your process or document it somehow, then measure it. Is it working? How well is it working? where is it failing, and then improve it based on the measurements of where it is failing. Here's an example from a real-life situation. We were producing software for a particular kind of situation, and we discovered that we were having a particular kind of bug very frequently during the integration and test phase. We analyzed why that bug was appearing so often. It turned out the bug was due to the fact that there was a new programming language being used, and there was a course given to all the employees in the new language, and there were mistakes in the course. The person teaching the course made some mistakes. The programmers new to the language just thought that was the way it was supposed to work, and therefore they were making all these mistakes, and the problem ended up showing up during integration. So the fundamental, what's called the root cause, was a bad training program. You see, a lot of the time people think, oh, it's just the programmers are doing bad code. No, it wasn't really that. It was something else. That's why you have to pay attention to what's underlying here. Okay, think about the process of cooking. How do you improve your cooking? You cook something, you make mistakes, you improve it, try it again. And once you get it right, you write it down and say, this is the way to do it. Although I'm reminded of a situation that happened, I was reading about it. This newly married woman started cooking dinner, and she was making pot roast. And she got a recipe from her grandmother. And the recipe said, use about 50 cents worth of stewing meat. Well, in the grandmother's day, 50% worth was a lot of meat. And so 50 years later, it wasn't nearly enough at all. But anyway, that's okay. The process automation principle says if you automate the wrong process, you do the wrong thing more efficiently. And this is, unfortunately, what happens all too often when people don't understand what they're doing. Here's another true story about this. Back in the 1980s, the Japanese automobile companies had made great inroads into the U.S. auto market. And one of the reasons was that their cars had a reputation for very high quality. And there was a visit made to a Japanese automobile factory by a bunch of executives from U.S. automobile companies. And they went over there, and all they saw was robots. So they went back and said, the solution is robots. So in the 1980s, they spent a lot of money on robots. It didn't really work. It worked just like this slide says. They did the wrong thing more efficiently. And the reason was because they didn't understand that the robots were only doing what the good process work told them to do. They had to know what they were supposed to do before they tried to automate it. They were trying to automate something without knowing what they were supposed to be doing. If you have a train that's running on a track and the track is about to fall off the edge of a cliff, you don't fix the problem by making the train go faster. That doesn't work. The productivity principle says if you design a process for perfect people, it will probably fail because most people aren't perfect. One of the things that you frequently run into in real life is people make mistakes. Years and years ago, my father ran a plant for Ford Motor Company that made paint and vinyl. And one of the problems when you make paint and vinyl is you want them to be the same color if they're in the same car. If you have a piece of vinyl on the side of the door and there's paint on the outside of the car, you want them to have more or less the same color. The problem is paint and vinyl are totally different materials. You put different chemicals in to make the color. So how do you make sure the colors are the same? The way they used to do it is they would hire people who had extremely good eyesight and very good color sensitivity. And they would look at the two and say, no, that's not right. This one's a little too blue and this one's a little more yellow. And they'd go back and they'd play around, and eventually they'd get one. They'd say, yeah, that looks pretty good. What he was able to do is, this was a very hit and miss operation. Sometimes the people thought they looked the same, except in a different light. They didn't look the same. He replaced it with a computerized device that, back in the early days of computers, that would look at the light spectrum coming off the reflection when they shone a light on the color and make sure that the spectrum was exactly the same. And then not only that, it could tell you what to do about the chemicals that went into the paint or the vinyl to make them more alike. And so he automated a process that was something humans aren't very good at. And as a result, produce much better quality results. So this is one of the concepts here. If you have a process that must be executed by people, keep in mind that people will make mistakes. A classic example in computers is you don't see the bug in your own code, but your neighbor can look at it and immediately say, hey, you left off a comma, or you left the parenthesis off, or whatever it might turn out to be. This is just human nature. It's human nature to make mistakes like that. So you have to have a way of developing software, for example, that calls for others to look at your code, not just give one person the responsibility to develop the code. Okay. Explain a few of these principles. That might be a possible exam question. And notice it says explain, not just cite the principle. Imagine explaining it to somebody you work with. Another possible exam question. Explain why automation alone is not likely to improve a company's real productivity and quality. I remember a time a guy came to my house. He was a cabinet maker, and he was making a built-in cabinet in my house. And he had a big collection of tools for doing his work. And I thought to myself, I don't even know how to use those tools, much less make effective use of them. Okay. Give an example in the software process where automation is a good idea, and then give an example where automation doesn't work very well. Well, that's a question for you to think through and think of a good answer for that one. Now, a lot of people say, well, software is not like manufacturing. And that's true. But many software experts think that software is more different than it really is. There's a human characteristic called a perception of uniqueness. The idea is you think your group is different from every other group. Your tribe, your village, your town, your country. You have all these reasons for thinking we are different from, and in many cases better than, the other one, whatever it might be. It's human nature to be this way. It has to do with our survival and all this kind of stuff. I think one way you see this is you go around Texas and you look at every little town has a football team, and they always think theirs is the best team until they actually play games, and then they realize maybe they're not so good. But this is just human nature. But the tendency to think of yourself as unique can lead you down blind alleys. For example, you say, we're different, so we have nothing to learn from the mistakes made by others. This is a common scenario with teenagers versus parents, right? Here's an interesting fact. Many of the most important scientific discoveries in history were made by people who were not considered experts in the field. A good example is what is known as continental drift, or technically it's called plate tectonics, the idea that continents move around. That idea came from a guy who was a weatherman. And the reason he figured it out is he looked at a map of a globe, actually, and he said, you know, these are like puzzle pieces, and you could move them all around and they'd all fit together like a puzzle. Like South America and Africa really fit just like that. The scientists of the time, the geologists and all the other scientists involved in this thought the guy was a crackpot. But it turns out he was right and they were wrong. Because he saw something that the others didn't see because they were so focused on their own discipline and their own preconceived notions of how things are. It's a very common human characteristic, and it's not limited to non-technical people. I remember when I was a young student, I used to think, oh, technical people don't have all those flaws that all those people in other fields do. But then as I grew up, I realized, yes, they do. They're just as bad. Okay. Einstein's theory of relativity is another example. That Einstein, what he did is he broke away from the conventional way of thinking. Now, software is unique in certain ways, and it is different. It's not really unique in other ways. In the next module, we're going to talk about that. To summarize this module, I told you we'd get out a little early tonight, so we're going to be a little early here. Process is central to effective software development. Effective management of software development requires paying attention to the process. And you're going to see that throughout the course. And basic principles of quality management do apply to software, but you have to pay attention to exactly how they apply. By the way, we're going to talk about work breakdown structures in a week or two. And so what you do in assignment 1 for now will probably have some mistakes in it, but hopefully you'll be learning new things that in a few weeks that will help. I'm doing it now because my real goal for assignment 1 is for you to read all the material required to understand the course. Okay. That's the end of Module 1. Let's take a break, and when everybody's back, I'll move back to Module 2. Okay, I will continue now with Module 2. Let's go back here. All right. I'm going to talk about characteristics of large software projects, what makes them different from small ones. Yes? Oh, okay. Well, should we wait for them? Okay. I'll wait for that student. I will... Well, if you can go find him. Is he here? Oh, there she is. Okay. We're going to go quickly to Module 2. Okay. Let's talk about characteristics of large software projects. Here are some differences. In a simple project, you know what operating system and computer you're going to use. On a large project, you may have a computer that is in development, it doesn't work yet, no operating system, no compiler or a very poor compiler, very poor documentation, and they're frequently making changes. I once developed a real-time operating system on a processor that had just come out of the factory, and I discovered all kinds of hardware bugs in the processor, and I had to design things around the hardware bugs. Software is largely independent of the rest of what's going on in a simple project. You're building an app for a phone, or you're building a game or something. In a big project, software is closely tied to other things. A network, a new computer, a set of equipment, some policies that are being executed on the part of the company. The end user is easy to contact on a small project very often. They're right over there, you ask them. In a big project, they may be represented by layers upon layers of other, what I call surrogates, people between you and the real end user. You can implement a little project with a few people. You may need a large team for a big project. An air traffic control system, a battleship, an airplane. These are examples of big projects. Here are some of the characteristics. They tend to be complex, not easy to understand. Leading edge technologies, safety critical, We're going to talk about all of these, by the way. With long product service life. They have to, imagine you're building software for NASA for a space thing that's going to be going out to outer space, and it's going to take 75 years to get to where it needs to get to. Are you going to be able to write something that'll last for 75 years? Severe operating conditions. I'll talk about that. And then the bureaucratic customer. Let's talk about these. Here are some examples of large, complex projects. Air traffic control system. This is a factory, a gigantic factory. This is a satellite system. This is a, what do they call it? It's a big computer farm thing. This is a ship with a helicopter doing search and rescue. These are all big deal projects. This might be your software team right here. Lots of people, millions of lines of code, many different companies may be involved. It's not just you and your team. Multiple locations around the globe. I remember one time I had to write some system software, and part of it was being written by a company in Sweden. And when they finally delivered the software, all the variable names were Swedish words, and we didn't know what they were. Think about all the different kinds of engineers besides the ones that you have in your classes, all the mechanical and civil and all the other ones. They may all be involved in developing this product, not to mention a lot of people in the business school and who knows what else. Now, what are some of the impacts of this size issue? Well, for one thing, you have more formality because you have to let everybody know what the rules are. It's like you have rules of the highway so that people don't run into each other. Well, it gets to be a really big problem with lots of people. You pay a lot more attention to the context in which the software is being used. For example, is there some unique network characteristics? Let's say you're building software for an automobile. Here's a problem I run into. I bought a new car about a year and a half ago, and it has a backup camera. But the backup camera won't turn on until after some other part of the electronics have booted up, and it takes about a minute for that to boot up. So if I'm in a parking space and I want to back out of the parking space, I can't get the backup camera until I turn on the car and wait about a minute. Why? Because somebody designed this thing without thinking about the fact that you might want to actually back out of a parking space without waiting a minute before you did it. Integrating the software team into the rest of the program. You can't just spend all your day talking to other software people. You have to worry about all these other people involved in the project. For example, somebody's designing equipment for running tests. You may have to be communicating with them, not only to figure out whether the equipment is going to enable you to do what you need to do for your software, but what about the scheduling of access to that test equipment? Maybe there's a bunch of people developing some hardware. They're assuming they're going to have access to the test equipment at the same time you need it. Well, you need to work that out. You need to pay attention to that sort of stuff. Or I had situations in my career where I had to deal with the people who worried about maintenance and support. I had to put in features in the software to enable them to do better maintenance and support, whereas normally I didn't pay attention to those people. So those are the kinds of things you have to worry about. Now let's talk about requirements. With a small project, you typically have a way of communicating with an end user. And very often they teach requirements in a university in a fashion that assumes you can directly communicate with the end user, or at least with somebody who knows what the requirements are. But in a real life, you have an end user, and then you have a lot of other people between you and the end user. A system engineer, a program manager, a champion. A champion is a person who's paying for the work to be done. I had a project one time where I was developing software for the U.S. Navy, and the particular software I was writing was needed by a guy in one of the Navy research labs. But there were about 8 people between me and the guy who needed the software. So I wasn't able to query the end user and find out what he really wanted. I had to go by formal documentation, which in some cases is not sufficient to explain what he wanted. I actually ended up having to figure out where he was going to go to a technical conference, go to the same technical conference, buttonhole the guy, and find out what he wanted. Because the mechanism was so bureaucratic. This is a common problem. You also have this conflicting views issue. Different people have different opinions. We're going to say more about that in a little bit. In a big system, there's usually a guy called a system engineer. In fact, they teach system engineers in the engineering management program here. Or a system analyst who designs the system. For example, let's say you're working on an airplane. And then the system engineer says, I'm designing the airplane, and he's got all this stuff related to the design of the airplane, and your job is to build the software for the landing gear. So the system engineer tells you what this landing gear is supposed to do, but you don't have any communication with the end user of the airplane. You don't even need it. What you need is to make sure that the system engineer is communicating clearly to you. And let's take a simple example. A landing gear, one of the rules for a landing gear is you don't go up if you're on the ground or if you're close to the ground. The landing gear has to be down if you're below a certain altitude. How do you find out what altitude you're at? And how do you test that when the altitude mechanism for the aircraft is still under development? Well, you have to work through all those things. You may also have to deal with suppliers or subcontractors, people who develop software under your direction. And then you have to put all those pieces together. How do you make sure they're all going to work together? What do you do about upgrades? For example, suppose you build some software that runs on Windows 7, and then out comes Windows 10, and you want to upgrade your product to work on Windows 10. But one of your suppliers says, well, we're not planning to upgrade to Windows 10 for 2 years. Or, even worse, you call them up and they've gone out of business. That can all happen with suppliers. Leading edge technology. This is what happens when your company is trying to be ahead of the other companies, and therefore you're using state-of-the-art technology. State-of-the-art technology often means it doesn't work right. We haven't got the bugs out yet. Often your product is a prototype, which may or may not work the way you want it to. Maybe it's never been done before and they're not sure they can get it done. I've worked on a number of projects where they couldn't get it to work right and the software had to fix the problem, even though it wasn't in the original specs. You have to know what's going on with all these other things and know it well enough that software can compensate for hardware problems. Software tools may not be very plentiful if you're building state-of-the-art systems. I worked on a project one time where we had to spend about $500,000 building a test set so we could test the software, because we were doing all sorts of state-of-the-art stuff that there was no devices out there to enable you to test. Maybe there's no compilers available for the operating system or for the computer you're using. Maybe the schedule keeps changing because of technical glitches that have nothing to do with software. Now we have another characteristic of complex, large projects, and that is often they are safety critical. Anything having to do with transportation, like a mass transit system or an air traffic control system. A lot of military systems are safety critical. Medical systems tend to be safety critical. You don't want to be responsible for somebody losing their life because your software had a bug in it. That's a big deal. And believe me, think about think about a modern car, something like 150 computers in a modern car. They all have software in them. Think about all the ways that software could screw up. Characteristics of safety critical products. Intense focus on figuring out how the system can fail. You spend a lot of time just saying, not just how can we make it work, but how could it fail? What if there's a power failure at such and such a point? Think about all the ways your PC fails. Fortunately, that's not safety critical. You wouldn't want to be flying on an airplane and have the pilot say, we're going to crash, folks, because my PC had to reboot. You know, you're not going to be happy about it, or it froze up, or, you know. Rigorous development processes. They tend to put a lot more attention to doing it right and doing it in a specific way. Independent audits. People come in and watch you and make sure you did it the way you're supposed to, which means you have to keep more records of what you did, and you have to make sure you follow the rules. This is especially true with aircraft, for example. If in the U.S., the Federal Aviation Administration won't let you fly the plane if you haven't followed a certain rules in developing the software. Same thing applies in other parts of the world. There's other agencies of comparable nature that won't let you fly that airplane if you don't follow certain rules. And you have safety standards that are out there that you have to satisfy. They have to do with interfaces and how you handle interrupts and all kinds of other stuff you have to pay attention to. I was once on a website. I was doing some safety critical work and I was searching for some term, and I happened to get on a blog from a group of people who were doing agile development. And the blog was basically, it started off with, I have the possibility of bidding on this government contract to build software for an aircraft. Should I bid on it? And the conversation that was going on was things like, you're actually going to have to document your requirements and you're going to have to follow these standards when you do the development. And the guy was saying, that's just ridiculous. I'm used to doing extreme programming. None of that was necessary with extreme programming. I don't want to have to do all that. And eventually, they were talking each other out of bidding on that contract because they would have to use a different kind of a process from the one they were used to doing. And I thought it was kind of funny because they apparently had never realized that there are projects that won't let them get away with the kinds of techniques that they had grown accustomed to. All right. What is a safety critical system and what can cause the thing to fail? Many times it's not the software specific, it's some connection between the end user and the way they behave and the environment. The end user does something that the programmer couldn't conceive of them doing that causes it to fail. Well, it's okay on a conventional software, okay, you got to reboot the computer, but in the case of a safety critical thing, you don't have that luxury. This is an example of an operating system for real-time safety critical systems. It's one called Integrity. There's several of them that are out there that are commercial that are carefully designed to partition the software into different sections so that the sections that are most safety critical can be focused on and done in more rigorous ways without requiring all that rigor for all the software. But in order to do that, you have to have certain rules about the way the software works and the way the operating system works. It costs you like $2 million to get that operating system because it's got all these security things built in. Let's take a look at long product service life. Typical commercial products are designed for service lives of maybe 5 years. Many large projects are going to have lives of 50 years. The B-52 airplane was developed in the 1950s and it's still flying. That's 70 years ago. And naturally, it's been upgraded a few times, but some of the NASA space equipment is using 1970s vintage computers and software written in assembly language for those computers. And today they use modern computers and emulate the 1970s vintage computers because they don't want to touch the software because they know it works and they don't want to play with it. I mean, that's the kind of stuff that you have to worry about. Suppose you're building software for a power plant. Power plants last 50 years. If you're controlling a nuclear power plant and making sure it doesn't blow up, you have to design the software to worry about that. Here's some examples of what you have to do. You have to think about, will my language and operating system be supported 30, 40, 50 years down the road? Because I'm going to have to do maintenance on this thing, and if there's no compilers available anymore, how am I going to do maintenance on it? One of the things you get into is making it really easy to maintain it, paying a lot of attention to that, and making it easy to implement upgrades when it's appropriate so you can maintain compatibility, which means, among other things, good documentation. I remember one year I had a bunch of students in this class who were in a maintenance organization of some company, and they said their biggest complaint about object-oriented design was that people didn't document their designs well enough, and then when they had to debug them, they couldn't figure out where anything was controlled and what was causing the problem, because there was so much information hiding going on and so little documentation explaining where things were done that they essentially had to undo the software to figure out how it was working because they hadn't designed it to be maintainable. So there's a lot of issues around maintenance and maintainability that you have to pay attention to when you have this kind of a product. What about severe operating conditions? For example, I once had to build something that had to function. It was in a military application. It had to be underwater for 24 hours, and then you would take it out and it would immediately function. It was some kind of a radio or something like that. Well, it wasn't so much a software thing, it was a hardware thing that was the big deal. You had to make it waterproof and you had to have all sorts of things that would make it function immediately and all this kind of stuff. But there were all kinds of recovery from problem scenarios where the software had to take care of it properly. The issue of how do you maintain software that is going to be on a device that's being used in the desert where it's really hot and it may be in the middle of a sandstorm. It may be that you can't just stick a thumb drive in a slot. Maybe that's too sandy and too much grit will get in the way and it won't work. So you may have to redesign things to use new techniques that aren't standard, aren't supported normally. There's all kinds of, think about something that's going to go on a probe that's going to land on Mars, that's going to run around for 10 years collecting data. You better make sure that it'll function well in that environment. Upgrades and maintenance should be easy to implement under difficult environmental conditions. This may mean, let's say it's going to be used in Antarctica. Well, in Antarctica, you have to keep mittens on your hands at all times or your fingers will freeze off. So cold. So a lot of the ways you would typically update, if a device had computer on it and you wanted to update the software, most techniques you would use for updating it, assuming it was not wireless, would involve sticking a device in a slot or something like that, and usually that's a little hard to do with a big mitten on. So you had to rethink these things, and you had to say, how are we going to make this function? Sometimes one of the problems is the hardware is low performance hardware, so it will be robust enough to survive very high temperatures or something like that, which means the software has to be extremely efficient because you're not using the fastest hardware around. You're using something that's slow but reliable. Wherever possible, avoid the need for maintenance. Design it very carefully. Give a lot of thought to that. I once worked on a project where we were building software that was used on ships. And these ships were out in the ocean looking for oil. The ships were 26 feet long. Kind of small for a ship, okay? if there was a bug in the software, and you had written that software, they would put you on a jet plane and fly you to the coast that was closest to the ship, put you on an helicopter, take you to the ship. You would then fix the bug. You would then be seasick for a week, because being on a 26-foot boat in the middle of the ocean makes you seasick. And then you'd stay on the boat until it went to port, because they weren't willing to pay to take you off. That was a very strong motivator for people never to have defective software, because they didn't want to spend 3 months on a ship out in the middle of the ocean. Believe me, it was not a pleasant experience. I knew a guy once who had to do it, and he could talk the captain into pulling close to the land in South Africa and letting him off in shallow water, and he ran up to the beach and then walked to the nearest town. He just wanted to get off that boat. So, believe me, it was a good motivator. Okay. Bureaucratic customer. This is a simplified version of the way the U.S. government acquires a major defense project, like, say, a new aircraft carrier. And that represents maybe a 15-year period of time. Each of the different colors represents a different phase of the project. Like I said, this is a simplified version. This is the next level of detail. Now, every box on that chart may represent something that takes multiple years. Now, you'll notice a lot of them are done in parallel, but nevertheless, it's a pretty complex process. And this can happen when you have a really complex problem. This is the kind of bureaucracy you run into if you're going to build any kind of major product for any kind of government, or if you're going to build something really complex like a new airplane, or any, it gets really complicated, and the implications are a lot of formality and attention to detail, because there's so many processes that go on and so many people who get involved, many kinds of approvals, many reviews, inspections, and audits, and sometimes there are political considerations. For example, when you work for a government, one of the most common things that happens if you have a contract with a government is they decide they don't have enough money. So they tell you, slow the project down so that we can afford to give you this year's money. So you have a project that you planned to get done in 3 years, and they make you stretch it out over 5 or 6 years. Most of the time in the commercial world, it doesn't work that way. They want you to get it done as fast as possible. But what happens is politicians approve things, and then they change things, which makes them more expensive. And then somebody else gets elected, and they have a different priority. And the next thing you know, it costs a whole lot more, and they have a lot less money. And therefore, they make you stretch it out. And everybody blames the contractor, but sometimes it's the politicians that are at fault, not the contractor. But anyway, that's the sort of thing that can happen. To summarize what I'm saying about large projects is they require more people, more formality, more paperwork, and so forth and so on, less direct contact with the customer, and less flexibility. You have to maybe follow very rigid structures. Now let's talk about a few myths and facts about software. Incidentally, just as a general comment, the way this course works, the very first week we talk about a lot of high-level concepts and principles. As we go along each week, we're going to focus in and get a lot more specific. You will find that out when you start working on assignment 1, by the way. But the point is that just because we're very high-level-ish today, next week we'll be more focused, and the week after that we'll be more focused. Okay. Here's what's called the super programmer myth. Software is creative, artistic. All you need to do it right is hire the most creative people you can find and leave them alone. You've probably heard this. there's a similar one, the creative genius myth. Creative people need freedom, not constraints and discipline. Just leave them alone and let them do their thing. Well, let's talk about this. Let's talk about art. Art is actually a very disciplined endeavor. A sculptor has to know how to sculpt out of the material so that it won't break, so that it'll do what he wants it to do. A person who's painting needs to know the characteristics of the paint, if they're watercolors or oil or whatever. And I remember a number of years ago, I was looking at a very old movie about Picasso. And they had a guy talking to Picasso about what made him unique and how he was different from other artists. And there was this one scene where they were walking along the streets of Paris, and it was a kind of a documentary film, and they saw these guys on the side of the street painting, and not only painting, but offering their painting for sale. And they asked Picasso, "Why are you more successful than these guys?" And he said, "They have as much talent as I do, but they don't have as much discipline." That was a very interesting statement that he made. And you find that true artists really have discipline. A painter needs to work with the specific characteristics of the paint. Think about a musician. A musician learns to play a particular instrument and learns the characteristics of that instrument. If you excel within your constraints, you are taking your creativity and applying it on top of a basic foundation of discipline and skill. You aren't just unconstrained. Unconstrained is a little baby playing with paints. An artist has a level of discipline upon which they apply their creative skill. The discipline, and the best explanation I ever heard of this is that discipline enables you to focus on what matters, what's called the critical few things, rather than the trivial many. If you read a review of a promising young artist, they will very often talk about having technical skill but not yet having the insight, or being creative but lacking technical skill. Whereas the seasoned artist has both. I remember a pianist, forget his name right now, but he was a famous Russian pianist who would go around Russia to all these little towns and play the piano in all these little towns. And he would play the piano in little rinky-dinky towns that didn't have a decent piano. And yet, he knew so much about pianos that he could play the piano and learn its weaknesses and compensate for those weaknesses when he did his concert, so that it sounded a whole lot better than that piano had ever sounded before, because he really understood his instrument. The same thing applies to just about anybody else who's a real expert at what they do. They understand their craft enough to, the way I describe it is, they know when not to follow the rules, because they know what causes the rules to be there and why they are there. And they know whether the conditions are such that you shouldn't follow the rules. It's like driving in icy conditions. Most drivers get into trouble because they follow the rules. And some of the rules you shouldn't follow when it's icy conditions, like jamming on the brakes when it's icy. Okay. Structure and discipline apply to the process of producing any product. You apply your creativity on top of the discipline, not instead of the discipline. And this is really where you get the difference between the true professional and the amateur. Airplane flight crews are very well trained, very disciplined, and yet they know how to take the creative action when necessary to avoid a severe situation. At least most of them do. One of the complaints about modern aircraft pilots is that too often they're automated too much. and they don't know how to handle the exceptional conditions because they haven't had to deal with them before. So there's a lot of discussion about that. Just because you follow a process and are disciplined doesn't mean you're not qualified, competent, creative, or any of that. It just means that you know how to build a foundation of fundamental skill and then apply your creativity on top of that. Same thing with athletic teams. Very often you see an athletic team that has very good players, but they don't win the games because they don't have a team-oriented discipline for how they play their game. Now here's another myth about software. The development tools myth. I would do a better job if you gave me a better computer. Now here's the home version. Your child comes to you and says, I'll get better grades if you give me a better computer. Now, you think about that and you realize, well, that could conceivably be true. But a lot of the time, the lack of a tool is not the root cause of the problem. It's you don't know what you're doing, you aren't spending the time to study, et cetera, et cetera, et cetera. The real professional knows how to use the tool properly. Giving a tool, think about the car we talked about earlier tonight, you know. You had somebody who didn't know how to drive very well, gave them a fancy car, and all they did is spend a lot of money. A good musician can make a poor instrument sound good. A good instrument cannot survive a poor musician. All you have to do is have a young child living next door who's learning to play any instrument, and you know what I mean. You know, they don't know how to play it well, so it sounds awful. Even if you buy them the world's most wonderful instrument, it's not going to solve their problem. They have to know what they're doing first. Good tools can make a difference when used by people who have experience and know what to do with them. You have to know what you're doing first. It's the process first, then the method, then the tool. Another myth about software, the gunslinger myth. Planning is a waste of time, just do it. Why should I spend money writing a plan? Do you want a plan or a product? Well, there's a very interesting book called Competing on Internet Time. It was written in 1998, just before the big telecom bust, by a guy named Cusimano. He's written a number of interesting books about technology. And he interviewed one of the guys who was one of the founders of Netscape, which is the predecessor of many of the modern software tools. David Stryker was the guy's name. And he said, saying that you shouldn't plan is BS. He says, you have to plan, but you have to plan intelligently and properly. You can't plan all the details at the beginning because a lot of them are going to change. The art of planning is saying, first of all, what are your goals? What are you trying to do? Secondly, what are your non-goals? What are you not trying to do? And make sure that you don't stray into the territory of trying to do things that are not your real objective. The non-goals are more important than the goals because you're making mid-course corrections all the time. One of the tendencies of technical people is they get clever ideas all the time. Wouldn't it be neat if we added this feature to our product? The problem is that feature isn't something the customer wants. It isn't something the customer is willing to pay for. And if you add that feature, you're adding risk to the project, you're adding more testing to the product, you're adding more problems, and you're not going to get paid for them. So a manager has to say, here is what we're trying to accomplish. Let's focus on that. Now let's talk about some facts about software. Software is very complex. I can remember how surprised some of my electrical engineering colleagues were when I showed them at one point in my career how complex some of the software was that was running on their computer. They thought their computer was complex till they saw the software. Then they realized, no, the computer isn't nearly as complex as the software that's running on it. Armies of people isn't the way to address a complex system. You have to think about how to manage it properly. You have to put a lot of thought into it. And it stems from fundamental laws of physics. For example, if you take a mouse and an elephant and you compare them the way a biologist would, one of the things you discover is that an elephant has internal organs that don't exist in the mouse. Why? Because the elephant is much bigger and much more complex and therefore needs organs that the mouse doesn't need. This is part of nature. The more complex you are, the more mechanism you have to institute. The higher percentage of your structure is for infrastructure. Here's another example. You take the bones of a mouse. They weigh, relative to the weight of the mouse, they weigh very little. You take the bones of an elephant, relative to the weight of the elephant, they weigh a fairly large percentage. Now, why is that? Because the strength of a bone is proportional to the square of the size of the bone, because it's the cross-section. But the weight it has to carry is proportional to the cube of the size. So the bones have to be proportionally larger to handle the extra weight. Now, that's another example where the infrastructure has to be larger and more complex because the organism is large. Now, that same principle applies to software. When software gets really big, the number of ways that it can interact with itself get to be much larger, and therefore you have a larger percentage of the software is devoted to infrastructure functions. We're going to see more about that a little bit later in the course. Here's another little fact. You can be as talented as you want to, but you have limited capacity. For example, if you wanted to paint the Golden Gate Bridge, the way to do it is not to hire the best painters in the world. You want to hire a large number of average quality painters who don't cost nearly as much, and you don't have to be a perfect painter, but you have to be able to do the sheer volume of work involved. Talented people are a risk to a project if you are in a position where you cannot live without them. If you're a manager and you have a person who works for you who you can't survive without, then you have a problem. What if they quit? What if they have a heart attack? We had a situation at Raytheon one time where a guy was an expert in optics, and he was the genius behind an infrared camera that we were building. And one fall afternoon, he was changing the oil in his car, the jack slipped, and he killed himself. Nobody knew what he knew. And we had a real problem. The following May, a young fellow shows up who had been this guy's intern the year before, and he had written software. Guess what? The guy who wrote the software knew how it worked, so he saved the company. This intern who just showed up by accident but happened to have been there the year before, and because he had written the software, he happened to understand how the stuff worked that nobody else in the company knew. Why did that happen? Because this guy was such a genius, nobody was willing to require him to write down what he knew. And then when something happened to him, you were in real trouble. This is another common problem that managers have to be aware of. This is what's called the strawberry shortcake example. If you have a strawberry shortcake recipe and it makes 4 servings, you can cut it in half for 2, you can double it for 8. But what if you have to serve 1,000 people? What are some of the problems you have to deal with 1,000 people? Well, where are you going to get enough strawberries and all the other ingredients? Where are you going to store them? How are you going to keep them cold enough? How are you going to find enough ovens to cook them all? How are you going to make sure everything comes out in the right sequence? In other words, you have to worry about management things when you have large numbers, even though you don't have to worry about them for small numbers, at least not nearly as much. When I was a summer intern I was actually in high school. I was a high school senior. I worked at Ford Motor Company. And I shared a little office cubicle with a guy who was a mechanical engineer. And he came in every morning, and he spent the morning working with a guy who was the expert on clutches at Ford Motor Company. And then he spent every afternoon sitting at the desk writing down what he had learned that morning. Now, why was this the case? Well, the guy who was the clutch expert thought that the fellow was only working half days. The company hired this kid and said, Mr. Clutch, I'll call him, is unwilling to tell anybody his secrets because he's afraid that we might force him to retire because he was fairly old. And the company was afraid the guy would get a heart attack and die, and they'd be without their expert on clutches. So this fellow, who was just like me, he was a summer intern, except he was a college student, he would hang around the clutch expert, and the clutch expert figured he was no threat. He would tell the kid all the stuff he knew, and then every afternoon he'd write down what he learned, so that the company would have a database of knowledge about how to design a clutch when Mr. Clutch quit or got a heart attack or retired or whatever he decided to do. And I learned an important lesson then, which is that it's really important not to be in a position where you are dependent on one person who, if they leave, your whole project is in trouble. If you have such a person, you need to say, what am I going to do if something happens to that person? And find a solution to that. Another fact about software is that it has a lot of unique characteristics that do make it difficult to develop software that you don't necessarily have these characteristics with other things. And one of the first ones is software does not have to follow the laws of physics. With a mechanical device, you can say, if I exert this much force, the worst that can happen is such and such. With software, you can make software do anything, right? I mean, that's why video games can have people walking through walls and all the other weird stuff that characters do in video games, because software doesn't have to follow those rules. That makes it very hard to test it, very hard to predict the possible ways it can fail. Discontinuities are very common in software, whereas they're rather exceptional in hardware. Things like extrapolation don't necessarily work. Now, I had an experience, again, early in my career, when they were discovering the speed of sound and trying to make airplanes that could go faster than the speed of sound. And one of the things they ran into was a bunch of them crashed because they didn't realize there were some discontinuities in the way a certain thing happened. And the formulas that were built into the subroutine library for those functions assumed that the behavior was the same below the speed of sound as it was above the speed of sound, when in fact it wasn't, because nobody had ever tried an airplane above the speed of sound before, and therefore they hadn't really had the problem. Another problem like this I ran into is you're navigating a ship and you're crossing the equator. Well, when you navigate a ship, you do all these calculations to figure out where you are. And this was in the pre-GPS days. Well, when you're trying to figure out where you are, you use a lot of trigonometric functions, right? What happens at the equator? A bunch of them go to infinity and a bunch of them go to 0. And a lot of formulas that involve x over y are infinity over 0 or 0 over infinity, and they end up with serious problems. So you have to worry about that kind of stuff with software, although the software works perfectly fine as long as you stay in the northern hemisphere or stay in the southern hemisphere. But if you cross the equator, everything goes haywire. That's an example of a kind of a problem you run into sometimes in software. How do you deal with the fact that software doesn't have to follow the laws of physics the way mechanical devices do? You have to understand the architecture a lot better. And you have to understand how changes are going to impact it. You have to preserve design descriptions somehow. This is something that people don't always realize when they build software the first time, is that what happens if we want to change the design 2 years from now in order to accommodate something new? will your design work correctly when you make that type of a change? Well, if you don't document that, people might not know, and they might make a change thinking it's perfectly fine, and it doesn't work. Possible exam question. Explain an aspect of software that makes it harder to develop correctly than other technical artifacts. Another fact is that software development is fun. People enjoy doing it. People love to program in many cases. They love finding a hard-to-find bug. Well, unfortunately, fun can translate into headaches for a manager. It's too easy for software to cost a lot more than it should because the programmers want to do all kinds of fun things to the software. For example, are you familiar with something called an Easter egg? It's where you have some weird combination of keystrokes causes something strange to happen that's got nothing to do with the purpose of the software, but the programmers put it in there just for fun. Well, think about it costs the company money to put that in there. It costs them money to test the software to make sure it works. It costs them, there's a risk that that might cause another problem somewhere along the way. The idea is to find a way to focus their creativity on the places where you need their creativity. Another interesting fact about software is how often it changes. This is a simple little chart representing kind of my experience in the software world. When I first got involved, I was in the 1960s, but I was often using computers developed in the 1950s. And I've lived through all of these changes. That's a lot of changes. If you think about it, every 10 years, the world is almost entirely different, the world of computers. And you can expect that to continue for the next 40, 50 years. And that means you have to think about how things are changing. You have to be able to figure out how to live with the new capabilities. Think about all the I/O devices that we've had in that period of time. When I started off, they were magnetic tapes that were about a foot big. Then they went to disks, and then they went to floppy disks, and then they went to smaller floppy disks, and then they went to CDs, and then they went to DVDs, and then they went to thumb drives, and who knows what they're going to have in a few years. That's just one little example. The infrastructure for software development changes just as frequently. The languages change, the tools change, the methods change. The way you do the debugging changes. The way you do testing changes. There's a lot in common, but the tools are, every 10 years, it's a whole new world again. Technical obsolescence occurs roughly every 5 years, according to many authors in the software community. What that means is that if you're in the software world and you're a manager, you have to say, should I use the technique that's 5 years old but good and solid and reliable, or should I use the brand new technique that looks like it's better except that it's all unproven and untried and risky? You have to know where to draw the line there. You have to keep abreast with change and avoid getting left behind, but avoid being too close to the leading edge where you just crash and burn all the time. Unless you want to have a career maintaining programs that are 30 or 40 years old. There are people who do that, but there aren't a whole lot of them. Another thing to keep in mind about change is that the fads are very common in software. And programmers love to try the latest thing. The question is it really going to work? I remember when I went from floppy disks that were 5 inches to the plastic floppy disks that were 3 inches, and the manager thought it was too risky to make that change. Well, from today's perspective, it doesn't sound risky, but from his perspective, it was something he wasn't familiar with. The software manager has to make a decision. Do I do the new thing or not? Because the new thing may have problems that you don't know about yet. Think about Microsoft. One of my rules of thumb about Microsoft is that every other operating system is a good one, and then the ones in between are bad ones. And if you go look at their history, you find that. Windows XP was good, Vista was not so good, Windows 7 is good, Windows 8 not so good, Windows 10 is hopefully going to be good. Well, you have to decide, at what point do I go to the new one? Is it worth it? Is it going to be one of the bad ones? And they're going to turn to you and say, which one should we use? And you're going to turn to your technical people and see what they say, and they're going to want to do the new one usually, whether it's good or not. Keep in mind that fads are very common in software. There are some fundamental principles that don't change, like human nature doesn't change. The theory of computer science doesn't change. I put a question mark after the nature of software, and the reason is that we understand the nature of software, but not as well as we think we do, and we're learning more all the time. So what we thought we knew 10 years ago may not quite be correct anymore. All right, to summarize, distinguish myths from facts when you're dealing with software, because it's very common for people to have beliefs that aren't really correct. Discipline is really important, even with an artistic development. And whether you're an artist or an engineer or something in between, it helps to have a foundation of discipline, process, and knowledge that you can build on, so you don't spend all your creativity reinventing wheels that already exist. Okay, that's the end of the module. That's the end of tonight's session. And I'll see you all next week, and have fun with your assignment 1.